If you run LLMs today, whether on a Cloud H100, a local RTX 3090 rig, or a Mac Studio, the specific architecture of your GPU determines which models you can run, how fast tokens generate, and whether you can serve multiple users at once. The GPU is no longer a black box. This is a complete technical breakdown of how NVIDIA GPUs actually work and why it matters for every AI engineer running local inference. A modern CPU core is a virtuoso soloist, optimized to run a single thread as fast as possible, with massive branch predictors, speculative execution, and deep out-of-order pipelines. A GPU core, by contrast, is a simple arithmetic unit. It executes instructions in order, has minimal cache, and can't speculate. Individually, it's slow, but a modern GPU has thousands of them, running in parallel. Deep learning is, at its core, matrix multiplication, and matrix multiply is fundamentally parallel. Every output element is independent of every other. A GPU with 10,000 cores can compute 10,000 dot products simultaneously. That's not marginal, it's 1,000 times the throughput of a CPU with 16 cores. NVIDIA GPUs aren't a flat pool of cores, they're organized in a strict hierarchy. At the top, the GPU die contains graphics processing clusters, each containing texture processing clusters. Inside, those are streaming multiprocessors, SMs, and that's where computation actually happens. The SM is the fundamental building block. Each one has its own scheduler, register file, shared memory, and execution units. The H100 has 80 SMs. The RTX 4090 has 128. The Blackwell B200 pushes 192. Inside each Hopper H100 SM, you'll find 128 CUDA cores for general arithmetic, 4 fourth-generation Tensor cores for matrix multiply, 32 load store units, and a 256 kilobyte register file that's the fastest storage on the chip. When you launch a CUDA kernel, execution is organized into threads, warps, blocks, and grids. The critical unit is the warp, 32 threads that execute the same instruction simultaneously. This is called SIMT, single instruction, multiple threads. When a warp issues a memory load that takes hundreds of cycles to return from VRAM, the warp scheduler doesn't stall. It switches to another warp that's ready to execute. When memory returns, the original warp gets scheduled again. This is latency hiding via warp switching, the GPU's killer feature. As long as enough warps are in flight, memory latency becomes invisible. The fraction of warps that are active relative to the maximum is called occupancy, and maximizing it is the core challenge of GPU kernel optimization. CUDA cores are general arithmetic units. They multiply and add floating point values one at a time. Tensor cores are fundamentally different. They perform an entire matrix multiply-cumulate operation in a single hardware instruction, D equals A times B plus C, where A, B, C, and D are small matrices. The whole operation, tens to hundreds of individual multiply-cumulates, happens in one clock cycle. Without tensor cores, an H100 delivers around 67 teraflops in FP32. With tensor cores in FP16, it delivers nearly 990 teraflops, a 14 times increase. Drop to INT8 and you get 1,979 tera operations per second. FP8, introduced with Hopper, pushes to nearly 4,000. When people quote GPU flop numbers, they almost always mean tensor core throughput, not CUDA core throughput. Verify which number you're comparing. GPU memory is organized in layers, from fastest to slowest. The register file at around 20 terabytes per second, zero latency, but tiny, private to each SM. Shared memory and L1 cache at around 15 terabytes per second, shared across threads in a block, configurable between 48 and 228 kilobytes per SM. The L2 cache at around 5 terabytes per second, shared across all SMs on the chip, about 50 megabytes on H100. Then VRAM, HBM, or GDDR at 0.9 to 4.8 terabytes per second. That's where model weights live. And finally, system RAM across PCIe at around 60 gigabytes per second. Crossing the PCIe bus is 50 to 80 times slower than VRAM. If any part of your model lands in system RAM during inference, performance collapses. Here's the fundamental insight for LLM inference. Flops don't matter. Memory bandwidth does. The concept is called arithmetic intensity, the ratio of floating point operations to bytes of memory accessed. When arithmetic intensity is low, your memory bandwidth bound, not compute bound. During autoregressive token generation, you generate one token at a time. Each token requires a full forward pass through all transformer layers. In each layer, the model's weight matrices, billions of parameters, must be loaded from VRAM into the SM's compute units. For batch size 1, you're multiplying a single vector against enormous weight matrices, very few flops relative to the gigabytes you had to load. A LLM 370 billion parameter model at BF16 weighs 280 gigabytes. At H100's 3.35 terabytes per second bandwidth, loading it takes around 83 milliseconds per token, about 12 tokens per second. The H200's 4.8 terabyte bandwidth makes it faster, not because of more flops, but because weights load faster. LLM inference has two completely different phases. Prefill processes the entire input prompt at once, all 2048 tokens simultaneously. The GPU computes Q, K, and V projections for all tokens in parallel, then the full attention score matrix. This is compute-intensive, large matrix multiplies, high arithmetic intensity, tensor cores running at full utilization. Prefill is compute-bound. Decode generates tokens one at a time. Each decode step processes exactly one new token. The matrix operations collapse to vector matrix products. Arithmetic intensity plummets. Decode is memory bandwidth bound. FlashAttention addresses this by restructuring attention computation to avoid materializing the full score matrix in VRAM. Instead, it tiles computation into blocks that fit in shared memory, reducing HBM reads and writes by 5 to 10 times for long contexts. PagedAttention, used in VLLM, treats the KV cache like virtual memory, managing a pool of fixed-size pages to eliminate fragmentation and maximize VRAM utilization for serving. Quantization is the primary lever for fitting large models into consumer hardware. The core insight is that 4-bit quantization achieves a 4 times reduction in model size with less than 1% quality degradation on most benchmarks. A model that requires 80 gigabytes at BF16 fits comfortably in 24 gigabytes at Q4. And running Q4 versus BF16 on the same GPU is 4 times faster because you load 4 times fewer bytes from VRAM per token. The Q4K-M format from Llama, CPP represents the sweet spot for most local inference workloads. Q6K is the quality sweet spot, nearly identical accuracy to FP16, with 60% of the size. The precision cascade also matters on tensor cores. Lower precision packs more operands into the same hardware lanes, which is why INT8 is twice as fast as FP16, and FP8 doubles that again. Quantization unlocks both capacity and throughput simultaneously. When choosing a GPU for local AI, 2 dimensions dominate. VRAM capacity determines which models fit, and memory bandwidth determines tokens per second. The RTX 3090 at 24 gigabytes and 936 gigabytes per second remains the best value for local inference, available used for around $700 to $900. The RTX 5090 at 32 gigabytes and 1.79 terabytes per second with GDDR7 is the new consumer king for 2025 and 2026. The Mac Studio M3 Ultra offers a unique proposition: 192 gigabytes of unified memory at 800 gigabytes per second. It runs models that no single GPU can touch, LLM 3.1405B at Q4, for example, but generates tokens more slowly than an H100 because of the bandwidth gap. For a 70 billion parameter model at Q4, the H100 gives roughly 45 to 65 tokens per second, 2 RTX 3090s give around 25 to 35, and the M3 Ultra lands between 12 and 18. Pick your GPU based on VRAM times bandwidth, not just flops. GPU architecture is evolving rapidly, driven almost entirely by AI workloads. NVIDIA's Blackwell GB200 NVLink rack connects 72 GPUs into a single unified memory space of 13.5 terabytes at 130 terabytes per second aggregate bandwidth, eliminating the internode bottlenecks that fragment large model deployments today. Apple and NVIDIA are converging on unified memory architectures, with NVLink chip-to-chip connecting Grace CPUs and Blackwell GPUs into coherent memory pools at server scale. Rust-based ML frameworks like Psionic and Hugging Face's Candle are enabling lower overhead kernel dispatch across heterogeneous hardware, CUDA, Metal, Web GPU, signaling that Python-only ML is ending. And photonic computing from companies like Lightmatter represents a genuine alternative trajectory, performing matrix multiplications with light rather than electrons, theoretically immune to the memory bandwidth bottleneck. The GPU is the most important piece of hardware in the AI stack right now. Understanding it makes you a better engineer. Full deep dive at ThinkSmart, Life/Research.